Hi guys, Dave here, G7IYK. This is a part of a series of videos that I'm putting together in an attempt to explain the functionality and also the sort of inner workings of this magnetic loop antenna controller that I've designed that we're sort of currently looking at on this video. Because I appreciate that not everybody would be completely familiar with all the component parts, or it would be beneficial just to go over each of the bits from a high level, just to familiarize anybody that might be interested with sort of how it works at a high level before going into all the nuts and bolts of each individual component part. So yeah, so we've turned it on, or actually I'll turn it off, and what happens is when I turn it back on, we'll get a splash screen, and then it'll go into the main menu. The splash screen only appears momentarily at the moment, because it's I could make it appear for longer. At the moment it's only a fraction of a second because it's sort of still in in development. So there's the splash screen and there's the main menu with a flashing cursor. Okay, so I thought we'd break this down into, let's go over the connectors on the board, sort of like the user connectors, and then what the sort of LEDs and buttons do, and then brief explanation of the sort of component parts of the component boards and how it's all sort of hooked together. Yeah, so without further ado, let's do buttons then. Well, I mean, obviously there's power, and there's the power switch I've just flicked on. So this is the main control board. I tend to build stuff in a modular sort of way. So this control board is something that I didn't build that. I bought that in. You can pick them up off eBay for sort of, they're pretty cheap, and they've got all the bits and bobs you need in a little development area on the bottom. They're kind of cool. Just saves time, really. I mean, there's nothing complicated about the way it's wired up. It's just, if I can pick one up for like £6-8, it just saves me, hours of messing about. So and it's got everything on there. So connector wise, this is a standard USB connector. Its use is twofold, really. It has a use as it gives the user the ability to reflash the microprocessor firmware via USB, so that you can update the firmware on the processor without a specialist PIC programmer using a bootloader which is running on the processor and then has a corresponding bootloader on as a PC application. I'll go over that in more detail in another video. And then the other main use is for controlling the board. You can use this loop controller standalone via menus and buttons using the board standalone, or if you want, you can plug it into the PC via USB, and then I've written a PC control application that pretty much mimics what you can do on the board, but using a PC. The idea behind that is that you could control the board and therefore tune your mag loop remotely without having to physically be at the board or at the tuner. That's a serial interface, just I2C. RS232 9-way standard 9-way D type. That's not actually used for the controller functionality. I use that for debug. When I'm debugging the software, I send messages over the serial interface to the PC and then display them on PuTTY or Teraterm or whatever, to allow me to develop the software or the firmware on the processor. It's an extremely common and powerful way of doing it. That connector and this header is used to program the PIC if you're not in development. So I tend to use a specialist PIC programmer called a PIC Kit 3. There's loads of them around. Pick them up pretty cheap, and you plug them into the PIC on a 5-way header, and that allows you to program the PIC in a matter of a few seconds. So that's that. This is power. Well, it could be power. I've actually routed the power in via one of these connectors that I've added to the board. There's a 6-way connector here. I'm actually only using 4 of them. I just happen to have 3-way ones lying about. 4 pins of that header are used to control or used to drive the mag loop stepper motor, if you're using a stepper motor. The stepper motor I'm using is a bipolar stepper motor, and that uses it's a 4-wire stepper motor. And if you were using a DC motor, then you would only use 2 of the pins. So that's all the connectors on that board. Obviously over here we've got 2 standard PL259 connectors. You can't quite see that, but they're labelled. This is where your ham radio would connect. This is where your rig goes, and this is where your mag loop goes. The idea being, if you're not tuning, if you're not in a tuning mode, this relay connects the radio to the antenna. So you just use the antenna as per normal, and then if you're in a tuning mode, the relay switches the radio out, and the antenna is then connected to the tuner. So you don't need to keep swapping connectors. It switches itself in and out automatically. I'll go over these RFE connectors in a bit. They're kind of internal. I mean, you wouldn't normally have all these pigtail leads flying about. If it was on a PCB, that would all be. They wouldn't be here. But I've just used pigtails to connect stuff up. I think that's all the connectors, really. Yeah. There's just some power connectors and other debug connectors I've got at the back here. They're just for debug, and again another debug connector down there, which is routing out the some analog signals. So let's do LEDs and buttons then. Now I should have labelled the LEDs and the buttons, but I suppose I got so familiar with them that I've sort of neglected to do that. But it's not difficult, so let's just go through them. These 2 LEDs on the left here are the sort of motor direction LEDs, so they tell you whether the motor's moving in, out, or left, right, depending whatever you want to call it. So as the motor moves, one of those LEDs will come on, never both. That LED is I call it the rate change LED. So you can move the motor using this. There's a rotary encoder here. This rotates round. You can move the motor using that rotary encoder, but you might want to change the rate at which the motor is moving. You might want it to move in fine steps or coarse steps. So what you can do is this rotary encoder's got a center button. So if you push the center, not in at the moment because we're not in the right mode, but when you press the center button, this LED will come on, and then when you rotate the rotary encoder, what you're doing is increasing the rate or decreasing the rate. So the motor won't move, it's just changing the rate at which it will move. Then when you press it again and the LED goes out, you can then move the motor at that new rate. So say you wanted to move it slower, you put it into rate change mode, spin anti-clockwise to reduce the rate, push it again, and now the motor will move correspondingly more slowly. I hope that makes sense. That LED there is the USB status LED. It's on at the moment because we've got no USB connected. If we connect the USB to a PC, once the USB 2 enumerates and the PIC is happy, the LED will go out. Hopefully, if it goes out, it means your USB is good. If it doesn't go out, you've got a problem with the USB. That flashing LED on the end there serves absolutely no purpose whatsoever. I call it the heartbeat LED. I always include one on any microprocessor-based project, and it's just a feel-good factor. It lets me know that the software is running, and also it's running at approximately the right rate. I mean, that's the sort of rate I flash it, and if it's flashing at that rate, I know the processor's running. It's a bit of a waste of time in this particular case because obviously we've got an LCD, so we know the software is running because we can see a flashing cursor and we've got stuff on the screen. But I just include it anyway. So button-wise, that's a reset button. Just to save me a quick powering it up and down, I can just press that button and it resets the processor and fires the software up again. There's 3 buttons here that are used to navigate the LCD menu system. So on the LCD at the moment we've got main menu and we've got 4 menu options: find loop, VSWR, cal, preset, move and config. So pressing the left hand button navigates down the menu system and pressing this button navigates up the menu system. And then this this button on the end selects the menu you've chosen. Oh, I should also point out the rotary encoder has another function. Some of the menus allow you to change frequency. There's frequency options you can change, like when you want where you want to move to, or presets. When you're in one of those modes, the rotary encoder is used to increment or decrement or increment a digit. So if you want to, if you want to increase from 0 to 9 or 9 down to 0, you can use the rotary encoder to change the digit, if that makes sense. I think that's all the buttons. So I thought we'd do next is just go quickly over the sort of component boards, the component parts. This is the way I tend to build most prototypes. If you look at other projects I've built on Instructables, for example, the Whisper beacon, built in a very similar way. So I tend to buy one of these matrix boards. They're dirt cheap, a couple of quid. It's not Vera board, if you know what Vera board it is. It's not a strip board underneath. It's just under each hole is a little pad, a little solder pad. They're not connected in any way. It's just like a matrix of them. So you just drop stuff in, and then you have to wire it up by hand, which is the way I like to do it. So all these boards, for example, this board here is actually you can just unplug it. It's sitting on little headers here on 1, 2, and then another one back there. So you can just unplug it because there's a whole shed load of wiring underneath this board as well as underneath the main matrix board. So yeah, this is the main control board, picked up pretty cheap, and so let's kind of go over what's on that board. That chip back there it was actually part of the board as purchased. That's all that is a serial interface buffer. Just connects the serial interface to the processor with some sort of sensible friendly buffers. That is the actual PIC. That's the microprocessor that's controlling everything. That's the microchip PIC 18F2550. Where do I start? Well, I'm not even going to attempt to start explaining what's in that processor. It's a 400 or 500 page document. The core of it is an 8-bit microprocessor with 32K of memory and a couple of K of RAM and some E squared. But there's a whole bucket load of peripherals, serial UART serial interface, I2C SPI, timers, counters, interrupt controllers, edge detectors, PWM controllers, not to mention a USB 1.2 interface module, all built in. There's a lot of stuff in there. I mean, I'm pretty much using most of it, to be honest. Almost maxed the memory out. Had to do a few little firmware snippings to get it to fit, including a bootloader. So yeah, it's running internally. It runs from this little. Not all the PIC microcontrollers run from an external crystal, but this one does. It's got a little 4 meg crystal here. Internally, it's running at 48 megahertz. That's called its FOSC frequency. That corresponds to an instruction rate of 12 million instructions per second. So divide by 4. The reason it runs at 48 meg is because you need 96 meg for the USB interface, which is double 48. So yeah, 48 is its max frequency, and say that's 12 million instructions per second. So it's pretty cool. And they're really cheap. They're like, what, 2 or 3 quid, £5 in one off. Unbelievable. They completely revolutionized the way you can go about making stuff. 20 years ago, this wouldn't have even been possible. They're just amazing. If you're going to build something electronics wise, just get a PIC. Don't even start thinking about making a discrete control system. It's just not worth the effort. Okay, so that's the PIC. Awesome. That's the motor controller for the stepper motor. I forget the name of the chip, the number of the chip. I'll put it later on. This is a little off the shelf thing. These are literally peanuts, a pound or two, and they control bipolar stepper motors. Driving bipolar stepper motors used to be a right pain, but this series of chips has made it really easy. I mean, really easy. You just give it a direction, pulse it, give it a micro step input, and then that's it. It's really, really simple. This chip here is what's the number? PCF8574. That is a Philips I/O expander. This is only a 28-pin processor. I needed quite a lot of I/O. I've got a lot of buttons. I've got also dedicated in serial interfaces and stuff. So I/O, when I mean GPIO or general purpose I/O, I mean pins I can use for buttons, LEDs, switching relays stuff, and I kind of almost ran out. Almost. So what I've done is I've added this. This hangs off the serial I2C interface, and basically it gives you another 8 I/O pins that you can use for input or output. And they're beefy enough to drive LEDs and stuff. And also there's another nice feature is that, for example, these buttons are hanging off of it. Rather than the processor has to keep polling the buttons to see if you've pushed a button, which is wasteful and time consuming. The buttons are hanging off this chip. When you push a button, this chip tells the processor that you've pushed a button. It's called an interrupt. So it interrupts the processor, so the processor doesn't have to waste time, keep checking all the time. So that's really cool. Again, they're really cheap. That's the rotary encoder that we've already been over before. It's a 2-bit grey code rotary controller. So there's only 2 bits, 2 connections out of it, and then the processor determines which way it's rotating by the order in which those pins toggle. Okay, right. Try not to talk too fast. I have a habit of doing that. Right, after the processor, this board here is the sort of guts of the thing. This tuner, in principle, works by sweeping a frequency presented to the antenna from, say, 3.5 megahertz all the way up to a maximum of about 29 megahertz. So you have to generate a frequency to sweep, and that's what this tiny little chip here is doing. That's SI5351. Again, it doesn't look like much, but there's a hell of a lot packed into that. It generates 3 possible clocks, all completely independent, from 2 PLLs on board. You can sweep up to something, I think it's up to 300 megahertz. You can run up to 300 megahertz. This one's running from it's got a 25 megahertz crystal, and it derives all its frequencies from that. So basically this is under microprocessor control. It doesn't do this automatically. The microprocessor is programming that over the I2C interface in real time. The calculations for the frequencies are performed in software. They're not looked up. They're calculated. It's a bit of, to be fair, it's a bit of a pig to program. I'm not gonna lie. It's a bit of a pig. It's brilliant, but it's not trivial to program, and it does chew up quite a lot of processor time. I previously used an older analog devices module, which is you see there's another row of headers here which aren't being used because I had a different module plugged in here to start with, and then I made a design change. I changed the way that this design worked in terms of the way it analysed the antenna, and I needed 2 frequencies, not 1. And so I swapped modules from the analog devices to the Silicon Labs frequency generators because I need 2 frequencies. So that's the frequency generator. They're obviously LCD. These are again really cool. I like the blue ones, backlit. Again, really cheap, £5. Traditionally, they're actually parallel. You can see the big row of pins here for parallel connections. They use an Hitachi chipset, quite old school, but you can get for next to nothing. There's a little board now that you can solder on to this parallel port, and it gives you again, I2C functionality. So you can't see the board; it's underneath. But it's just got a I2C to parallel interface. It actually uses one of these. So you can set the LCD up using I2C, which saves a lot of I/O. Over here we've got this is the, as I've mentioned before, this is the antenna switch, Omron relay. This is the solid state switch. It's a bit of a massive, well, it's not a bit, it's a huge overkill. I just happen to have this power transistor is like ridiculously huge for switching a relay. It's an RF 9501 P channel FET. I just got a bunch of them lying around from a previous project, so I just used it. That's an optical isolator because this is 12 volts. I don't want it's actually been driven from this I/O expander, which is running at 5 volts, as is the processor. I didn't want the 5 volt. I don't want the 5 volt system in any way connected to the 12 volt system. So this is an optically isolated transistor. So the processor controls the I/O expander. The I/O expander controls the opto isolator. The opto isolator controls the switch, and the switch switches a relay. It's basically what happens there. Now, this bad boy. So as you can see, I've built this. Oh God, the time I've spent getting this right. This is my second attempt. This is the antenna bridge and signal processing. So this is what's taking the output frequencies from the frequency synthesizer and then presenting them to the antenna. So 2 frequencies in, antenna out. And what this allows you to do, or allows the processor to do, is to find the resonant point of the antenna and also measure the VSWR of the antenna. Now, the first attempt I had at this used a completely different bridge design. So there's a bridge here. I'll explain in another video and a bit of paper what the bridge is doing, but it's a balanced bridge. Now this bridge here is completely passive, so it only has resistive elements. There's no capacitors, there's no reactive elements in this bridge at all. Now the previous design I came up with did have reactive elements, it had capacitors in it. And what I found was that because the bridge had reactive elements in it, the previous design, when you presented that to the antenna, it actually, the capacitive components or the reactive components in the bridge changed very slightly, subtly changed by only a few kilohertz or maybe 5 or 10 kilohertz, but they moved the antenna resonant point. So basically the thing you're using to do the measuring changed the thing that you were measuring, if that makes sense. So I couldn't, and it changed, and the amount it changed it depended on what frequency you were analyzing. It was I tried in software to fix it, but in the end I scrapped the whole bridge and started again with a different design. This design has only got resistive elements. There's no capacitors in that resistive bridge, so it doesn't affect the antenna. It doesn't change the antenna resonant point when you connect it to the antenna. So how it basically works is, I'll go through this in more detail in another video, but how it basically works is you've got 2 frequencies here. This one here on the left, that's your fundamental. So that's the frequency you're trying to analyze, like 7 meg on 14 meg. That's the frequency you're trying to, either you're trying to tune to or you're searching with. This frequency here is the fundamental minus 100 kilohertz. It's always minus 100 kilohertz. So no matter what frequency you change the fundamental to, this is always 100 kilohertz lower. And the reason for that is the signal that's reflected from the antenna, I'm mixing down to an IF of 100 kilohertz. So these 2 natty little parts here are NE612N double balance mixers. So they are mixing down the reflected signal, or the reflected signal from the antenna, which would be at the fundamental. They're mixing that down to 100 kilohertz, and it doesn't matter which frequency you are analyzing or which frequency you've swept to or where you are, the output of the double balance mixtures always has an IF of 100 kilohertz. And the reason for that is that there are capacitive elements, reactive elements, after the double balance mixers, and I always want those reactive elements to behave in the same way, so they always see 100 kilohertz no matter what frequency you're on, if that makes sense. So basically I'm mixing down to 100 kilohertz. These are MCP 6002 general purpose operational amplifiers. There's 2 operational amplifiers in each package, so 2 in there and 2 in there. What this chain does the forward path, this does a reflected path. And the first operational amplifier is being used is what I would call it's a rectifier. I'm using it as a perfect rectifier. So it has a diode in it, but the operational amplifier has is wrapped around the diode, which allows the diode to operate at very low signal levels. And then the second operational amplifier is simply a buffer, a gain buffer, and then there's a trimmer on the gain buffer for the forward, and there's a trimmer on the gain buffer for the reflected. So you can set the levels, and there's a calibration routine in here to allow you to twiddle these and set them up. So that's for being able to calculate VSWR. I've done my best. This is not a VSWR meter, but it's pretty close to I think the VSWR is pretty close. I've measured it using a proper VSWR meter, and it's pretty close. To be honest, every VSWR meter I use produces a slightly different result. So I've got 3 VSWR meters and a nano VNA, and if you connect them to the antenna, you get a slightly different result no matter what VSWR meter you use. So this is no different. But it gives you a pretty good indication of what your VSWR is. Let me think. That was a lot of wittering, and I hope I didn't speak too fast. I tend to get carried away. I think I've pretty much covered everything on the board now. So yeah, if you've listened to that much wittering, then maybe you'll want to know a bit more about how it works. I'm going to go through in other videos and in the Instructable kind of a bit more detail about how the firmware works, and the mechanism for how the tuner works from from a firmware point of view, and in a little bit more detail about how this antenna bridge and processing stage works. I probably won't go into too much detail about the signal generator because it's all documented anyway. It's really nice, just a bit of a pig to program. Okay, I think that's enough because my throat's hurting now. Thanks for watching. Cheers, and I'll see you again.